I'm Stephanie Marcus from the Science, Technology, and Business Division here at the library. I want to welcome you to our lecture today. We are going to spend a day on Titan, and it's going to be really cold, so your LL Bean parkas are not going to do you any good at minus, 288 degrees? Fahrenheit, which is what we're used to. Yes, so this ought to be fun. Recently, we were cleaning out our files in my division, and they were really old, but we're trying to be way modern. So we're throwing out all the old things and keeping a few things that looked interesting for historical purposes. And I took the Saturn folder, and it was filled with pamphlets from NASA on the Pioneer mission and the Voyager missions. And I found one on Titan. Actually, there was a Washington Post special supplement all about Titan, and it was dated December 1980. So none of you, well, at least you kids, were not here. And I just want to read you what it said. Near the end, it says, Titan has now become a prime candidate for a future space mission. One idea already being toyed with is to put a spacecraft in orbit around Titan, then float a balloon in its atmosphere and land a small robot on its frozen ocean surface. If Carl Sagan is correct and the ocean is liquid, the robot lander would radio that fact back before it sinks into the ammonia and water seas. Can a mission that difficult be made to work? Well, you probably heard that last year the Cassini-Huygens mission ended with the spacecraft plunging into the atmosphere of Saturn, but in 2005 it had landed the Huygens probe on the surface of Titan. So today we have Melissa Traynor from NASA, who has gotten that data and has been working on this and can tell us what she has learned and what they plan for the future. I'll have to tell you who she is. She's a research space scientist and the associate lab chief of the Planetary Environments Lab at NASA Goddard out in Greenbelt, Maryland. She earned her BA in chemistry at Franklin and Marshall College in Lancaster, Pennsylvania, and then got her PhD in chemistry at the University of Colorado, Boulder. So please help me welcome Melissa Traynor to the Library of Congress.
All right, well, thank you. Thank you so much, Stephanie, and to the Library of Congress for inviting me here. I'm so delighted to be here and to be talking to you all today, and I'm just so excited about the audience that I have here, including all of you students. So thank you guys for spending part of your trip to the Capitol here listening to my lecture. So as we just mentioned, we learned a lot about Titan since 1980. That vision of a mission architecture that was described in that article of the orbiter and the balloon and the surface lander didn't totally come to fruition, but I'll discuss a little bit about what the Cassini-Huygens mission was like and what it found. Spoiler alert, no oceans of methane or ethane all over the surface, but there are lakes near the poles, so there were places that we could have splashed down. So I'm going to spend some time talking about, as I said, the science of Titan, what we've learned about Titan, and then what are some future exploration options for our next step to learn more about Titan. And that's a mission concept that's currently in work right now that I'm a part of called the Dragonfly Mission. So I'll give you one group's vision of what we should be doing at Titan next. So information about Titan. It is the largest of Saturn's moons. There are 62 of them, but you can see in this sort of family portrait that it is the largest by far. And it was discovered originally in 1655 by Christian Huygens, the namesake for the probe that we sent there. And it's actually the second largest moon in the whole solar system after Ganymede, which is a moon of Jupiter. The exploration of Titan, harkening back, again, here's an image from Voyager, when Voyager did its flyby through the solar system, Voyager 1, and we could see there was previous data that there was likely an atmosphere around Titan, just based on how it looked through telescopes, through ground-based observation. And that was confirmed in 1944 by retrieving spectra of the moon that showed gases were present in the atmosphere, and that includes methane. And then we got this photo here, and you can see Titan looks like this fuzzy ball, and then we can see these layers up high in the atmosphere. That tells us that there's not only gases in the atmosphere, but also solid particles. You can think of them as sort of a haze or a smog, and this comes from photochemistry that takes place up high in the atmosphere. And so this kicks off this idea that Titan is, well, we like to think of it as this organic factory. We have some methane gas, so that's CH4, carbon with 4 hydrogens. And then there's nitrogen, and the chemistry that's induced with those gases, with either sunlight or energetic electrons coming in the top of the atmosphere, starts this synthesis of these really large organic molecules. And we're only just sort of learning what they are. But because of that, you have organic chemistry abound. And we think about habitability and what it might be important for life in a location, in a planetary environment. That's one of the big criteria we think of, because we know our own biochemistry, you and me and the trees and everything that we eat, is made up of carbon chemistry. And so we think that is at least one view of what is needed for life as we know it. And so Titan is, abound in it. Mars, we're going and we're looking for little tiny pieces of it in the rocks, but Titan's full of it. The other thing that's cool about Titan is that it's actually the only moon in the solar system that has a substantial atmosphere at all. And what's interesting is it's also mostly a background of nitrogen gas, which should sound somewhat familiar because that's the background gas that we have in the Earth's atmosphere here too. Let's see, it's mostly nitrogen. It has a few % of the methane and then also some hydrogen. As I mentioned, it's the only satellite that has a dense atmosphere. You can see here's this Ganymede. That's the one that's just slightly bigger. These are the Galilean satellites around Jupiter. And then it also has the second highest surface pressure of all the solid bodies. Okay, so what does that mean? Its surface pressure is actually greater than Earth. It has a denser atmosphere than Earth. 1.5 times, if you were standing on the surface of Titan, it'd be 1.5 times the pressure as we experience on the surface of Earth. Much less dense, though, than Venus. Venus is the winner of the terrestrial bodies in our solar system. But many of the other bodies compared to here, Mars has a much thinner atmosphere, and then the Moon and Mercury, et cetera, are considered airless bodies. Exploration of Titan, as we discussed, Pioneer flybys in '79, Voyager 1 and Voyager 2 in the very early '80s were able to fly by and get images such as you see here. This look that Titan has in this type of view, it's sort of this fuzzy orange ball. That was all we could see for a very long time. And that's because of this haze, these particulates that are in the atmosphere. The atmosphere is very thick and it's hard to see down to the surface. So we think often of Titan as having been behind a veil prior to the Cassini-Huygens mission, when we were really able to get up close and personal and get an idea of what was hiding underneath. And this is why we weren't sure. Maybe, some chemical model suggested that the whole surface could be an ocean. And we weren't entirely sure what we were going to find on the surface until we were able to go. There was some imaging showing surface features with telescopes, and these were both taken after Cassini either had been designed or after it was on its way and at Saturn, just showing differences in the surface reflection and giving us an idea. Okay, it's not a homogeneous surface. There are some differences here, but we don't really know, well, what are they and what is the surface made of? Here are just some facts for Titan, just to give you an idea of the average diameter is about 5,000 kilometers. The surface gravity, I always like to mention that, it's about 1/7 that of Earth, right? So if you weigh something like 150 pounds on Earth, you'd weigh 21 pounds on Titan, and everything else would feel lighter. The surface pressure I mentioned is greater than that of Earth's. And as Stephanie pointed out, it's very, very cold there. So I often think in kelvins when I go to low temperatures as a temperature unit. 94 kelvins, what is to the rest of us who think about weather, right? Minus 290 Fahrenheit would be the temperature there. Yes, so you're going to need a lot more than a North Face parka. And then the other really cool thing, because it's so cold, I love this Earth analogy for Titan. The bedrock there is actually made of water ice and not silicate rock like we have on Earth. But you can think of it in some ways as an equivalence. So it's so cold that the frozen water is as hard as rock. But if you had some kind of volcano, we'll talk about cryovolcanos, or lava erupting, instead of it being molten rock, it could be water ice or other liquids that contain a water composition. So there's a lot of similarities to the way that rock behaves on Earth, water ice on Titan. And that's going to come important later when we talk more about prebiotic chemistry. Another thing, the Cassini mission wasn't an orbiter around Titan, but it did do many, many flybys, and I'll show all of those in a moment. We discovered that Titan is what we would call an ocean world, and that's because it has an interior liquid water ocean. And we could just tell this as the orbiter is flying by and making very precise measurements with how far it is from Earth and how it's kind of getting tugged and pulled by the tidal forces around Titan. We could see that it has variable tidal forces, which tells us there is liquid in that center. And as I mentioned, making the analogy to Earth, in this case, it would be liquid water, or primarily liquid water. And so this cross-section is our current prediction of what we think that interior looks like. So you would have a global subsurface ocean. It'd be covered in this ice shell. We're not sure how thick that is. And that is sort of what we think of as the bedrock or the crust. And then we have this atmosphere making all these organic molecules, and those rain down on the surface, and they coat the surface sort of like a soil. So you've got this organic soil on top of this really frozen water ice. And again, I mentioned habitability, and we mentioned things that we consider ingredients for life. Organic molecules and other nutrients are part of that, but water is always part of that too, at least for life as we know it. And Titan always inspires conversations about life as we don't know it, but we'll put that over here for now. Is that now we've got organics, and we have this potential for some kind of liquid water to be mixing with those organics. And that starts to sound a lot more about what we picture in a habitable environment. But it's very, very cold, so we'll talk in a minute about, well, how do you actually get that mixing? So a little bit more info on the Cassini Orbiter and the Huygens probe. So this picture here, see with the person for scale, this is the probe inside its little aeroshell. And then here it is bolted to the side of the orbiter. The orbiter is huge, and there's sort of a desk chair and a desk down here that gives you a little bit of a sense of scale. And then this is a diagram that just points out where several of the scientific instruments are. So again, the Huygens probe is on the side. Cassini was an orbiter around Saturn, and then when it got into the right position, it launched that probe towards Titan, and then used the rest of its instruments to study Saturn and the whole Saturnian system for the time that it was in orbit. These shows all of the orbits that Cassini made around Saturn, all these different lines, and I tried to highlight here the Titan's orbit. So Saturn's here in the middle, here's Titan's orbit, so you can see many of those flybys were near Titan at different distances. And every time we got close to Titan, we had the ability to do imaging or radar measurements or compositional measurements of the upper atmosphere. And that's how we've learned everything that we could. And these numbered 126 close flybys of Titan. So flybys we consider that were sufficient to get a lot of good information. Talk a little about the year, Saturn, and Titan. So Saturn's year is 29.5 of our Earth years, so close to 30. And Titan travels with Saturn, so Titan's year is the exact same length. Saturn has an axial tilt that also provides Titan's tilt relative to the sun. And so because of that, Titan is going to have seasons just like we experience here on Earth. They're just going to be a lot slower. So you can see these dates here. The northern winter solstice in October 2002, and they didn't get to the spring equinox until 2009, right? So that's a really extended year. Titan's day is defined by its orbit around Saturn. And another fun fact, that Titan is tidally locked in a synchronous rotation with Saturn, which is similar to our own moon to us. So if you can't sit on Saturn, but if you could sit on Saturn and gaze at Titan in the sky, you'd always see the same side of Titan, just like we always see the same side of our moon. So this graphic here kind of shows the orbit of Saturn and therefore Titan going around the sun, and what the Cassini mission looks like in terms of a single Saturn year. You see, it didn't even complete that full year. This is kind of another fun way to think about it. You won't be able to read it, but this gives you the idea of, again, from the perspective of a Saturn year, if we relate that to our year, it's as if Cassini arrived in mid-January and crashed into Saturn in late June. So again, not even a full year, just a part of what it was like. So when we think about observing long-term trends, we hadn't really even been there for an entire year. So a lot of times when we see something, we can make predictions about how it might repeat, but Cassini itself is not going to be able to satisfy our knowledge for whether or not those predictions are correct. Here's some nice views of Titan. With the imaging science subsystem, this is sort of a full color image. Again, you see that orange ball. But if we look at certain key windows in the spectrum where we can see all the way through that atmosphere, past those particles down to the surface, you can start to see some more surface features. Here's another view, the VIM spectrometer, visual and imaging mapping spectrometer, that we've used to learn a lot about the Titan surface. So depending and what wavelengths you're looking in and how you're studying it, it's how we've been able to sort of penetrate that veil that I mentioned to learn more about Titan. Here's a map that was generated at those infrared wavelengths, and we'll call out some more of these features in more detail, but this is how we start to get a picture of what Titan is actually like. All these differences between dark and bright are places where the light is either reflected strongly or absorbed. We infer a lot of information about compositional differences. We may not know exactly what this material is, but we can say that this is not the same thing as this because they look different, right, in this image. A couple things we'll notice, and I'll show closer pictures, is we have this band of darker material across the equator, right? We can see small features that start to look like craters in there. And again, not a global ocean. You can kind of see in this image some peppering, though, of what we discovered were lakes near the pole, especially near the northern pole, larger seas, really. This is just another image using radar. So we overlay radar measurements on those visual images, and that gives us better information on the topography and where something might actually be a different altitude or have a different roughness, in addition to just having a different light interaction. So here's one of the really cool things we found looking at those belts around the equator. We found sand dunes, and we all experience. Many of you may have been near sand dunes on Earth, so you kind of have a feel of what sand dunes are like. Now on Titan, the sand, again, isn't going to be a ground up silicate rock or like we're used to on Earth. In this case, what we suspect it is the organic material that's raining down, these particulates raining down from the sky, and some kind of physical interaction might lead to them growing into larger particles and blowing around and forming these dune structures. Maybe there's some water ice mingled in there. We're not entirely sure what they are, but we can make a lot of inferences based on their direction and how they are shaped and how they move on about how big they might be, because we have some ideas of how windy it could be on Titan. And so here I just love some of these images. A little harder to see on the projector. Hopefully those of you at the screen can see better. So we have this whole narrow belt of sand dunes, and then again under these sand dunes in places, interdune spaces, sort of where the sand dune comes down, we expect that there's access to that water ice bedrock there in between those. We also see impact craters. Now Titan has a very thick atmosphere, which is going to slow down and burn up enough small impactors that you're not going to get peppered dots everywhere like you do on places like Mercury or the moon and airless bodies. So on Titan, we only see impact craters that are pretty large, that made all the way to the surface. And then the other interesting thing, again, because Titan has this dense atmosphere, we already see sand dunes, so we know there's sort of the interaction of wind erosion on the surface. We learned that it rains on Titan occasionally. In this case, it rains methane rain, not water rain, because Titan's so cold that methane actually is the substance that can appear in ice and liquid and gas. Because of that, we have the ability, Titan has the ability to erode things like impact craters. So then we can study these impact craters and learn about how they've been transformed over time, possibly by the Titan environment. And again, it's for a lot of us, we're talking about crazy things, methane rain and organic sand and maybe cryovolcanoes of water and ammonia. So it sounds really exotic, but at the same time, these are very familiar features and very familiar processes to those of us who study the Earth and study other planets. And I think that's partly why I love Titan so much and why people are so fascinated with it. And so with an impact crater, what we expect to happen is you have an impact, And again, if you have enough energy put into that water ice crust, just like on Earth, you could get melted rock in an impact. On Titan, you get melted water coming from the impact. And if it's a big enough impact and you deliver enough energy, you could have melted water present on the surface for actually really long periods of time, maybe 10,000 years, maybe more than that, depending on the size of the impactor. So as cold as it is, we do have this possibility that there have been periods in the past with transient liquid water on the surface. And so again, let's take all those organics that are made in the atmosphere. Maybe they're around, they're coating the surface when this impact comes in, and now you've got a melt pool, and you have this potential for a lot of interesting chemistry. Here's some other tectonic features. We know that we see mountains kind of along here in these areas. Here's some other, they're not super tall mountains, although this one actually 10,000 feet, that's nothing to sneeze at. That's a decent sized mountain. So we see a lot of topography on the Titan surface. So now this idea of cryovolcanism is one of those things I heard someone say, you can say it in a room of Titan scientists and you'll start a fight because no one can agree on whether it happens or not, but it's certainly possible. And so we've been searching for evidence in the imaging data and the radar data to see if it's possibly there. This is one feature that's been pointed to as possible evidence where we see what looks like a central dome and possibly flows that are overlaying and interfering with dune structures. And so that could be a potential cryovolcano. And again, we're interested in that because that's another opportunity, melted water coming out and over onto the surface, or water ammonia mixtures. So as cold as Titan is, there's this potential to have water coming out and placing on the surface and interacting with the environment. This shows a different view of what that image looks like. Again, what looks like potentially a volcanic crater in there. And we see channels. We see lots of channels that we think are the evidence of fluvial action. So rain coming down and forming streams and flowing into maybe temporary lakes or seas on the surface, depending on the season. This is one of my favorite ones here. I mean, if I just changed the color on that, you couldn't tell me that wasn't Earth, right? A river channel on Earth. But in this case, it would be liquid methane raining on the surface and flowing around. And again, we discovered lakes and seas, particularly around the North Pole. This is a good image here. This lake here, Ligeia Mare, is pretty close to the size of Lake Superior in the United States. This is a very lake or sea, it depends on your perspective, but it's a very substantial body of water. And these other ones down here have connectors where it's actually a significant system there. I actually, years and years ago, was part of a mission concept to study lander that was really a boat that would splash down into one of those lakes and float around and take measurements. So the Huygens probe, that was another way that we got a view of the surface. This was a probe that was released, I said, from Cassini and floated down through the atmosphere of Titan, as you see, partly on parachute, and landed on the surface. And it took measurements, chemical measurements and images on its whole way down, and then it lived on the surface for about 70 minutes afterwards. And this is one of the main photos that it got from the surface, kind of sitting and looking out. And these pebbles that we see, these are thought to be, again, made of water ice that have been eroded into round pebbles somehow. And I think this one's probably just a couple centimeters across. You have a very, skewed perspective looking from just the eye camera of the lander. But here's kind of a fun image showing with the moon, an equivalent type perspective of the moon surface with a similar scale. So that gives you an idea. That's a footprint, what the size that is. We've also noticed, as I mentioned, rain, cloud, and weather patterns because Titan has thick atmosphere, and it has the methane, which serves as similar to a hydrological cycle. On Earth, we see things like convective clouds and thunderstorms and rain events, and we were actually able to witness, this image just shows clouds, and I don't think I have a picture here, but we were actually able to witness a rain event through observations of Titan, where you could see kind of a cloud come in, and then after it was gone, the ground looked wetter or darker, and then after some time, it looked back to the lighter color again, which suggests, again, soaking of the ground and then drying out of the ground. So again, similar, but really different, right? It's kind of Titan's a fascinating place. And then again, get back to the complex organic chemistry. So this was hinted at even before we arrived at Titan. Just by looking at that haze and looking at the spectral features, we could tell there was a lot of carbon, nitrogen bonds in there. And here, in our flybys of Titan, a lot of them were actually close enough into the atmosphere. We have an instrument called the mass spectrometer that can sniff in the gas as well as the very small particles and look at their composition. And what we see, and also visually see, just lots of molecules that kind of look like that. And I don't know how far any of you have gone in organic chemistry, right? So you've got all these like the ball and stick models here showing carbons and hydrogens. So we see things like propane or that you might use, to barbecue, acetylene, hydrogen cyanide, right? That's not a good one. We do see a little bit of carbon dioxide, things like that we can confirm definitively. And then we also see what this spectrum is kind of telling you is that there's a lot of complex molecules going far out. They just get bigger and bigger and bigger and bigger. So as I mentioned, this organic engine, this big synthesis process. But part of our questions are, these molecules and the kinds of things we make when we just start adding carbons and hydrogens and these long chains, right? That's a lot more like gasoline, like a gasoline slick you might come across, right? It's not necessarily what we think of when we think of prebiotic chemistry. And so part of our question is, at some point, can we get to the level of complexity where you have more like oxygens going in there, things that look more like amino acids or nucleobases, or the types of molecules that we think of as the kind of complexity that's more similar to biochemistry. And that's just an open question that we have about Titan. Again, these measurements are made about 1,000 kilometers up, way, way up, not at the surface. This is another graphic that kind of captures where does Titan sit in the solar system in terms of this complex organic chemistry, right? It's actually got other than Earth, the most complex organic cycle that we know about in the solar system. And so this is a comparison, this graphic, of the level of complexity of molecules on these left bars in terms of the size of how big they are that we've measured, as well as the abundance. And if you look at, Titan has a lot of molecules, but they're pretty small. We looked at a place like Venus. Venus has a lot of carbon and carbon dioxide, but not big molecules here. Again, same thing for Mars, lots of carbon and carbon dioxide, but so far we've only measured a couple small molecules. Earth, we know, obviously we can measure it the best because we're all here with our fancy instruments, but we know it has big, big molecules, the kinds of things that in our DNA. And Titan, again, we know it has these really big complex molecules. We know it has a lot of it. And then the question is, but exactly what are they all like? And can we find molecules in there that might be of interest from more of the prebiotic chemistry and astrobiology perspective? All right, so this is just, again, a cartoon, just to kind of bring it, I keep saying it, that's just because it's so exciting. Titan, it's this mysterious moon, right? It's covered with all these unusual materials, these exotic materials. You're talking about methane rain, you're talking about ammonia water volcanoes, but at the same time, there's so many features about it that are so similar to our own Earth. And we can study geology there and learn a lot about what's going on there just by making comparisons to what we already know, and the atmospheric processes, and as well as this methane cycle, and how often does it really rain, and we've only seen a small part of the year. Do you have other periods? Do we have a rainy period maybe where the south gets lots of lakes and seas? And then finally, we're interested in studying Titan from its astrobiology perspective. Again, carbon and water, and we have sunlight. We have all these ingredients we tend to think of. And one thing I'll point out, myself and lots of other scientists love going into lab and trying to mimic the chemistry that you see on Titan. So we build these chambers and we irradiate them with sunlight or blast them with electrons, and we can make complex organics. They just kind of look like that look a lot, have a lot of similar features to those based on what we can see at Titan. And what a lot of experimenters have shown is that if you take those complex molecules and you put them in water or water ammonia mixers and you hydrolyze them, and you're just very, very patient. And so what we do is we tend to run them at warmer temperatures to speed up reactions that could take actually like millions of years or 10,000 years. We know that we can see evidence of a very interesting prebiotic chemistry. So things like amino acids and nucleobases has been shown in the lab that you can make those things if you just have those organics sitting in water and you can wait a while. And so we kind of want to know, well, I can do that in a lab, but is that really what's happening on Titan? So where would we go to look for this kind of biochemistry or prebiotic molecules or biomolecules, whatever we want to call it. So we'd want to look at places where we think organics and water have in some way intermingled. And so this is a very complicated cartoon, but it has highlights a couple things. So we've got this possibility of our deep ocean and our ice crust with organics on the surface. And if we have any cryovolcanoes and cryolava and placing on the surface, then there's places where it would intermingle organics and water on the surface there. This doesn't show a specific impact, but I kind of painted that picture. If you have an impactor come in, you have this impact melt mingling and more stuff depositing in it, then that's another place you could expect to find evidence of this kind of chemistry, maybe in a frozen over impact melt. And then what we really don't know, is there a connection between the surface and this deep ocean? Like on Earth, we have places where there's volcanoes, where there's what we call subduction zones, where you can have this cycling. We don't know if this happens on Titan. We have no idea. We don't even know how thick this crust is, so we don't know if there's places where kind of you get any connection, or they totally separate it. We don't know the answer to that question. But if there was some kind of connection, you could imagine some really fascinating stuff going on in this deep ocean. So the next step, we have learned so much, as I said, from Cassini and from Huygens, that has basically just brought us more questions, right? Every time we go, we learn more that makes us want to go back but now we know better some of the things we're looking for, right? We know we're not going to splash down in a 10-meter global ocean. And so some of the questions that we're asking, I've kind of been starting to pose them. What makes any planet or moon habitable? Is Titan, would we call Titan habitable from a certain perspective? And what chemical processes led to the development of life? Carl Sagan, who was referenced earlier, he really loved Titan because he liked to think about it as this frozen prebiotic Earth. So this idea, if we could go back to Earth billions and billions of years ago before life was everywhere, there might have been a chemistry going on in the atmosphere and on the surface that resembled something of what Titan's like today. It's like if you took it and you were able to move it way out and just freeze it in place. We don't know for sure if that is a true analogy, but what we do know is that at Titan we have evidence of this immense global scale organic chemistry and all these fascinating things that are happening. But can that ever get you closer to a biochemistry or life? We don't know the answer to that question, and we don't really know how life formed on Earth. But by learning what the extent of that possibility is in an environment that appears to have all the ingredients, that's going to teach us a lot about what that process looks like. Now, I make the case that, like Carl Sagan did, Titan is the ideal place to go look for these things, because we do think we have all the ingredients for life as we know it there. There's energy. We know there's sunlight. There's a lot of energy deposited in the surface, the top of the atmosphere. We have lots of organics. We know we have abundant, complex organics everywhere. We also know we have a liquid medium, right? We always say life needs water. Life as we know it needs water. That's because that's the solvent that all our biochemistry takes place, right? We're all just bags of water walking around with a little chemistry going on. So we know that there is liquid water deep in the subsurface. We think there are times it has been on the surface. But there's also liquid methane. And that gets us into that whole other, Pandora's box. Well, what if you had life and liquid methane? And it's a fun thing to think about. It's a little harder to think about, well, but how would we know, right? It's going to look very different. But there we can draw a lot of parallels to what kind of complexity and what kind of patterns we expect to see in an advanced chemistry that could be going on in a different liquid medium. And then there's also the potential that the organics on the surface are mingling with that interior ocean, and that's another place where you could look for really interesting chemistry taking place in liquid water. And again, even aside from this whole prebiotic chemistry question, Titan's a fascinating place to study because it's got this methane cycle. It's a lot like the Earth's water cycle, but it's different, right? And it's going to have its own differences, and we can learn just a lot about how planetary systems operate in general. And I don't know how many people here are interested in things like exoplanets, but as we look out among the other stars and think about exotic worlds around those other stars, right? We want to understand as much as we can. We're just getting these little dots of spectra from them to understand what they're like, but we also want to have in our back pocket a whole catalog of understanding how environments operate with XYZ conditions. And so Titan is a more prevalent type of environment than an Earth is. And we'd want to understand what is that environment like and learn more about those planets out there. So again, this is sort of this case that we like to make is Titan itself, it's an ocean world, and it's also this fascinating laboratory. It's already been doing these experiments for us, right? It's been producing these organic molecules for millions or billions of years, right? It's had all this time to do those reactions on the surface that people are doing in the lab. And all we really just need to do is go and try to make those measurements and sort of pick up the results that Titan has already been generating for us. And I'll just point out this. I like this graphic. It kind of shows what do we know about Titan. Here we know we have complex chemistry upper in the atmosphere. We think we can get small biomolecules like amino acids, but then can we get down to anything that looks like an autocatalytic system or the complexity of biochemistry? No, we really don't. We don't know. But because we're this far on this path, it gives us enough of a reason to want to go and find out. Okay, so another thing about Titan, I mentioned those the surface diversity you could see in those images. We don't truly know what the composition of all those surface features are, but we do know that there's a lot of different kinds of surface features. And we'd think of those, like on Earth, as different geologic units, right? What's the difference between going to the desert, going to the rainforest, or going to, just here where we live in Maryland? We don't know what all these places are, but because we can tell that they're different, we'd want to be able to visit a variety of locations to understand which compositional units might have the most interest for habitability or for prebiotic chemistry environment. And so the Huygens probe, of course, has landed in one of them, and it was there, and it was wherever it landed, right? But ideally, what we would want is to go to all of these places and to be able to visit all of these locations and understand how they're different and understand how they all play into that story of Titan. And so one thing we've made the big case is that mobility on the surface is really key to us fully understanding what the different settings are like and what does that mean for Titan's habitability. So we do this on other planets, right? We do this on Mars. We send rovers that can visit different places and aren't stuck in one spot and can take different samples and teach us something about a location. Our paradigm on Mars is to rove, drive around. They can cause problems sometimes, holes in the wheels, if anyone followed this story of Curiosity, although she's doing better now. And also, it's kind of slow. I'm actually on the science team for Curiosity as well, and I'll tell you some days it's like, and that's it, right? That's as far as she goes in a day. Titan, it turns out, has a lot of advantages over Mars, which help us think a little bit more out of the box. I mentioned the atmosphere is a lot denser than Earth's. Between being colder and higher pressure, you actually have a really dense atmosphere that makes aviation or flight of any kind, whether it's airplanes or hot air balloons, makes that a lot easier because, again, it's easier just to go up. The other thing is, I mentioned the gravity is a lot lower. And again, as you can imagine, if you were on Titan, you could jump a lot higher with the same leg strength, right? So with, again, any kind of airplane or whatever, you would need a lot less energy to get lift. And so those are two things that tell us it would be a lot easier to fly on Titan. This cartoon, which only some of you can see, it kind of summarizes what I'm saying, right? On Titan, you could definitely easily fly, just like you do on Earth. Mars, much harder, right? There's just a very thin atmosphere. It's really hard to fly around. So we want to take advantage of that. We want to fly on Titan, and that's how we could visit all these different surface locations, and we could cover a lot more of the globe that way if we're able to gain that kind of mobility. And so that's going to lead me into talking a particular mission concept. This one is called Dragonfly. That's a team I'm working with to develop a concept for the next round of exploration of Titan. It's not the only way you could solve this problem, but it's one that our team is particularly fond of. And the idea is that you see in this image, it's a drone. It's a dual quadcopter, which is a fancy way of saying it has 8 rotors, one on each corner up and down. And it's actually not too different in size from a Mars rover. So it's big enough to carry full instrument payload. But again, because of the lower gravity, the denser atmosphere, you're able to move that payload around on the surface, even as far as like tens of kilometers apart in just a short amount of time. And so we'd be able to visit all those different environments. So again, the idea is not to fly all the time. The idea is to hop, right? So you go to a place and you sit there for a while and you investigate it very thoroughly. Let's say we're in the dunes. We would try to scoop up some of that sand. We take meteorological measurements and see how windy it is and watch and see if we can see dune sands blowing around to understand what are they made of and how often are those dunes migrating. And then when we're ready to move on, we would fly to a new location and perform that same in-depth investigation at the new location. So again, most of the time is actually spent on the ground, but you have this capability to move around. All right, so what would we want to do there? So the things that I think you'd want to do on the Titan surface are sort of broadly listed here. I've hit a lot on the prebiotic chemistry. You may have noticed I got my degree in chemistry, so that's where my focus is. We'd want to look for evidence in some of these environments, the impact craters, et cetera, for the types of molecules that could be relevant for life. So, I just mentioned things like amino acids or nucleobases that form our DNA. We would just in general want to understand the composition. Maybe we land in an impact crater melt and we're able to dig into that ice and see what kind of molecules could have been formed when that was once water. We would also be looking for things like patterns in molecules. This is an abiotic pattern. This represents something you'd find in biology. We see very specific patterns in Earth, life on Earth. And we'd also look for things like chirality, and people are very familiar, but chirality is a lot of molecules can be mirror images of each other, but they have a handedness. They're either turned, we call them left-handed, or right-handed, right? And so on Earth and our bodies, right, the amino acids that we have are all biased towards one side or another, and that imbalance is a signature that we believe is specific to life. And if you just make amino acids a synthesis, or if you find them in a comet or something, they generally tend to just be what we call a racemic mixture and not tilt it so much one way or the other, indicated in this graph. And so we'd be looking for any differences. We don't know actually how that arose in life on Earth, and so we'd be just looking for a difference like that in this environment. We'd also just want context and composition. Are we sitting on a giant block of ice or not? Are we sitting on a big lump of organics? What's around us? What is everything made of? We have a couple ways that we just get that kind of context. One is a gamma ray spectrometer that can sort of bounce neutrons off of the surface and investigate, again, whether we are near a water ice layer or an organic layer, and get a general idea of the composition here, just as we're sitting and sensing the ground. And then also, when flying around or when up close on the surface, we get a lot of images. And again, images will give us a good idea for the geologic context. These are dune features on Earth, but we think that they're good analogs for what exists on Titan. We can see macroscopically what do the materials look like on that surface, and how do they compare to the types of materials that we think they are, and are they sticky, or are they like powdery, like cornstarch? What are those materials like? And then we also have a package for meteorology. We would want to do winds and temperature and just learn more about the environment for an extended period of time. And geophysics, the ability to kind of sense what is the ground surface like, as well as maybe penetrate and get an idea of interior structure, and can we get a sense of how thick that ice layer is. So all the things that you can only do on the ground, up close and personal, right? You have to be there on the surface. So this particular mission concept is in consideration by NASA under what we call the New Frontiers project. So if it were selected next year, then what would happen is we would launch in 2025. So it gives us time to build it and get it ready to launch it. And we would not arrive to Titan until 2034. So half this audience here, you guys should do that math, because you would probably be like primely set up to be major contributors of the science team for this mission by the time it actually showed up. People like me, will be all old and gray by then. And the idea is we want to land in those interdunes, those dunes we talked about, those dunes near the equator. And we'd want to look at the dune material, and we'd want to look at those interlayer dunes where we think it's very icy. And it would actually be not that different of a location from where Huygens landed. And so what's nice about that is we know something about that area because the probe landed there and we have lots of good images. But then once we're there, the probe actually does its own reconnaissance. The lander, because as it ability to fly, it could go up high, look around itself, picture a drone, and then it can come back down. Then it can go up high and fly a little this way, fly back, come back to the same place, but now we've mapped that route to very high resolution, and now we know, okay, well, that place over there is the safe place to land. And that's how we could do hops along the surface without necessarily having super high resolution imagery from orbit. You don't really need an orbiter first if you can do your own mapping, right? And so that's kind of how the mission, you can picture it leapfrogging itself around the surface, but eventually migrating to all of these different types of surface places. So one thing I have been getting questions on, and I thought I might, maybe for this audience, so I want to mention a new discovery coming back from Titan recently. It's actually, you can't read the dates on these, but it's not that new data. But the example of Cassini, we're going to have discoveries coming from Cassini, even though it's crashed into Saturn, for years and years and years and years, because there's always so much data that we collect at planetary bodies, and it takes a long time to understand it and to process it, and sometimes it takes a new person to come along. Again, one of the students here in the audience, maybe 10 years from now, will look at it and say, this is interesting, I have a question about this, and dig in a little deeper and learn something new. People are still doing that with Voyager data, with Galileo data. So once, it's kind of being in a library, mentioning that, right? Once this data has been collected, it's archived for everybody. NASA archives all of this data. And then for future generations can still look at that data to try to understand as much as we possibly can. So this is an example of something, data from back in 2009 and 2010 has been looked at, and we think there was a dust storm. Now, we just came out of a dust storm on Mars with the Curiosity rover, so this is something, as for many of us who work on multi-planets, something that was already on our mind. This idea there could have been a dust storm on Titan as well. And that just comes from looking at spectral features that brighten and darken, but then based on the location and the type of movement that we've seen, and trying to model it and understand it. This idea that this could have been a dust storm that created with something winds higher than normal. In this case on Titan, that would be something about 4 to 25 mile per hour winds, lofting up that dune material, we think, or organic dust, and blowing it around. In this location, the artist concept is on the right. It's kind of a fanciful view of what this might look like if you'd been sitting on Titan looking at the dust storm. And so this is the kind of thing the surface mission that I'm talking about may not actually experience that. It's in part because the thought is that it would only occur during the equinox. You have to have the solar energy crossing the equator to trigger the right conditions to generate these winds to make this storm. So that wouldn't time exactly right with our mission concept. But that prediction could be wrong too, right? So it's possible that future missions that do go either in orbit or on Titan or on the surface might observe similar features to this. And so I just thought that's pretty cool new news. But never fear about the Dragonfly lander if we win, because much like Curiosity, we're not solar powered, we're nuclear powered. And so if there were a dust storm, we wouldn't have to worry about dust covering our solar panels. And like Curiosity, you just kind of sit there for a little bit and then you wait, and then eventually you can start moving again. All right, so again, just in summary, Titan itself is a really fascinating place. I think the more we learn about it, the more we want to go back and learn more. And this particular mission concept you've described, and I have a little video, is one way that we could do that. I think it's a really exciting way that we could explore Titan. And so I'm keeping my fingers crossed that we get to fly Dragonfly. And I didn't know if I mentioned the duration, but we would be there for over 2 Earth years on the surface. So again, it would be very similar to like a Mars rover mission, just taking a lot of time to learn a lot about the surface there at Titan. I just want to reference, if you want to learn more about that mission in particular, and also some more about Titan, there's this website here for the Dragonfly mission, just thanks to the mission PI, Zibby Turtle, who provided a lot of these slides for me. I don't want to take credit for them all. And then I wanted to show a quick video, if I can figure out how to do this on the computer. Let's see. It's kind of a fun video to imagine what it will be like. Make the bars go away. So this would be coming in, landing, and it would sort of fly itself down to the surface, and cruise through the interdunes. It wouldn't have its own camera drone following it around, though. We would we would just get the first-person perspective through all the imaging on the drone itself. And then land, put up its antenna to talk to Earth, do surface science, and then decide where it's going next, and then take off and fly away. So before I open up to any questions, though, I also want to mention, okay, Titan's a moon of Saturn, right? We all have our own beloved moon that we can see up and close much more often. Next Saturday, October 20th, unfortunately I didn't have a lot of these to hand out, but is International Observe the Moon Night. This happens every year, and the idea is there's groups all around the globe taking time to look up and observe the moon and think about lunar science and accomplishments of humankind and visiting the moon, et cetera. And there's a hashtag observe the moon or moon.nasa.gov/observe. And if you're interested, I can share that. I apologize I didn't have more handouts. But I recommend for everybody, those of you who are local, there are big events up at Goddard Space Flight Center. But for those of you who are not, you should look into, there's other events all over the place to celebrate the moon. And I know at Goddard we're doing fun activities to think about lunar science, maybe cratering experiments. And they always do something with candy because everyone loves candy. So that's one big thing. And then in the back, for those who didn't get them, I did bring some handouts with images of the moon. We're coming up. It's the anniversary of the Apollo program, 50th anniversaries. We're kind of hitting lots of different milestones with the history of that program and celebrating, again, that accomplishment and then everything that we've learned about the moon since and lunar missions since then. And feel free to pick those up at the back. And I also have pretty pictures of Saturn, too, my favorite image of Saturn, where it's eclipsing the sun and just kind of looks like it's glowing from behind. So with that, I'm happy to take any questions.
I just want to say, if you would repeat the question.
Okay.
Yes. So please ask your questions.
Yes.
How long is the Dragonfly designed to last, and why did the lander that originally landed not last very long?
Oh, good question. Okay, so the question is, how long is Dragonfly expected to last? And why didn't the Huygens lander last longer? So I'll answer the second one first. It was not designed to. So the Huygens was designed as a probe, not a lander. So the idea is it was on batteries and it had enough battery power to make measurements. It took about 2 hours to float. I always say float because it seems so gentle. On Mars, we just crush it. Float through the atmosphere, take chemical measurements and visual measurements while it went down. And then everything we got on the surface was not guaranteed. Because at the time, it really was thought it was possible it would splash into an ocean and drown, maybe. And so it actually lasted longer than it was expected to. Dragonfly itself, I'll give a caveat to any questions about this mission. It's under competition still, and so there's a limit to what I can say about it. But the planned nominal mission is over 2 years, and we always add many design factors on that. And so it will be designed to last much longer than that. Yes.
Since the atmosphere is thicker and there's now, of course, meteorological events that take place, what type of impact do you think that would take on the drone that the rovers, for instance, on Mars might have to face, such as weather patterns, wind velocities?
Mm-hmm. Okay, so the question is, we know that there's things like wind. We know there's a thicker atmosphere. And so what kind of impact could that have on an organic material blowing around on the lander? And how does that compare to Mars and the things that the rovers? So the biggest difference there is just the density of the atmosphere. Because there's a denser atmosphere, there's more energy in the wind. But in general, with the exception of this potential death storm that we think we observed, the winds on Titan are expected to be fairly low. About less than 1 meter per second, particularly in these areas. It's been, it's not meant to be weaseling out, but it's something that the experts in Titan meteorology are on our team and are actively engaged in the design and making sure that it would be robust against any of those conditions. The most important thing to remember is that we aren't flying most of the time. Most of the time, we're just sitting on the surface. And so, like any good pilot would, we will only fly when conditions are safe and appropriate. And the organic material, actually, the conditions of Titan and the dust would probably not behave that differently than dust that's blowing around on Mars, than silicate dust on Mars. Yes, Stephanie.
There's always this concern about contamination of moons and other planets
Mm-hmm.
and the fuel that's used, so I wondered how you're going to address that.
So the question is about contamination of moons and planets and the types of fuel that we bring and how will that be addressed. So this is, NASA handles this, we call it Planetary Protection. And so there's an officer in an office in NASA headquarters that thinks about the conditions that we observe on different bodies that we might visit and what are the standards that we need to hold our spacecraft to when we send them there for concerns about things like forward contamination. And what's interesting is all the different bodies in the solar system are classified at different levels of risk. And then you go to a place like Mars and different areas of the surface are classified as different areas of risk. So for example, we have the same nuclear power source that we'd proposed for this drone on Titan is what's sitting on Curiosity rover at the equator of Mars right now. Because of where it's sitting on the surface, it's considered far enough away from any potential liquid water, which is where microbes might be living, that it was deemed okay. If you go further north to the polar regions where there are ice caps, you wouldn't necessarily be able to do that right now. And then depending on where you go, you're held to a different standard of cleanliness on just the material itself. So it turns out that right now, given everything we know about Titan, it's at a different class than these regions on Mars are. And so we have a strict set of procedures that we have to follow for Titan, and we're able to do that with this mission. It is possible that when we go and we learn a lot more about it, that we may find out that maybe it is in a different classification, but right now, based on what we know, we have a set guideline that we have to sort of clean the rover to, and we're able to use the nuclear power source.
Will there be enough plutonium by 2020?
That is definitely above my pay grade question. The question is, will there be enough plutonium for us to put it on this drone? When the opportunity to propose a mission was put out by NASA, they said there would be, and that we were allowed to propose this power source. So that's what we're told. So we're hoping so. That's kind of on upper level NASA to work out for us. Yes.
Are there any hopes, is there any places on the surface where there are any eruptions where there's a chance of sampling any of the liquid?
That's a good question. So the question, I think it was that. The question is, are there places on the surface where there could be a chance of us actually witnessing an eruption, a cryovolcano eruption, and then sampling that eruption? I would say we don't know enough about the likelihood or prevalence of cryovolcanism. Again, some people don't actually believe it happens. It's sort of controversial to be able to predict that. However, should we stumble upon it, that would be phenomenal, right? A great opportunity, so we can just hope. Yes. Back.
Is this presentation online anywhere? Because I know a lot of people who wish they could have been here.
It will be, it's been recorded. And so the question is the presentation online? So if you're watching it online, you know the answer. It should be recorded and archived, and I believe the materials I'll be sharing as well. Yes.
What's the ultimate goal of this project? Is it to figure out what makes life possible, or just to learn more about the solar system?
So the question is, what is the ultimate goal of this project, the particular project I'm pointing to, or really other exploration of Titan, to find out what makes life possible, or just to learn more about the solar system? So the answer is yes. It's all those things, right? So that's what we're always trying to do. And every time we go to a new place and we ask new questions and get new data, we kind of learn a little bit more on all of those goals. So the idea is this mission does help to address our questions about what makes a place habitable. What ingredients do you need for life, and where could we find them? And that's all toward this longer goal of, are we alone in the universe, right? This is a big, just human question that NASA has taken on as part of its mission. And in the same time you're looking at that, you're learning more about the solar system, and we're learning more about environments. And this is another thing I always like to point out. I may be a planetary scientist, but my favorite planet is Earth because I live here, and so do all the people I love. And every time we go out and explore a new environment in the solar system, we actually learn more about our own planet too, right? Because we build all our models, and everything we understand about how Earth works is based on a data point of Earth, one, right? And when we go to new places and we get new data, we can try to understand how those fundamental processes work. And it's easy to tell if we're wrong, if we make incorrect predictions based on what we think we understand about how things work. And so actually exploring new planets and trying to model new planets is some of the most progress is made towards better understanding our own planet and our own climate. So all of those things I would think of are part of the goals that this mission addresses. Part of those goals. Those are big goals that we have for NASA. But great question, yes. Oh, such good questions. Okay, let me get them all right. So the question is, on Mars, we know the atmosphere has been lost, stripped over time. It doesn't have a magnetosphere, and so the sun has stripped away a lot of the atmosphere, and that's partly why it's a lot colder and drier than it was in the past. How come that hasn't happened at Titan is one question. And is there talk of terraforming Titan? Okay, so the top level answer, Saturn has a giant magnetosphere. It actually interacts a lot with the Titan atmosphere, and we think that that's part of where some of the chemistry comes from in the atmosphere of Titan. So partly Titan is protected by that, but there's a lot of things that we don't actually totally understand about Titan's atmosphere. So why is it so thick? Right? How is it held on to that atmosphere when it's got low gravity? That's a big question I always get. Where did the methane come from, and has it been there all along, or was it just there for a temporary amount of time? So there's a lot of questions that we still have about Titan's atmosphere that I think we need more explanation to be able to answer. Has it always been, maybe it was thicker and lost some of it. We don't really know for sure the whole history there. Terraforming Titan would be an enormous challenge just because it is so cold, right? And there's a lot of ways, Mars, with all of its shortcomings, it's closer to the sun. It's still a lot more familiar to Earth, and there is water there, et cetera, and it's sure a lot closer. So, and if you caught that, it will take us 9 years to get this mission out to Titan, and that's just the small little robot. Getting everything you would need, even just to have a human presence on Mars, is daunting. And so the idea of getting everything out there to Titan, more so. But I'm sure there are people thinking about it. Yes.
NASA's currently planning to put humans on Mars, but far in the future, is it possible to put humans on Titan? And would there be any advantages to having humans rather than robots on Titan?
There are always advantages to having humans in an environment doing the exploration. From the science point of view, right? You and I could walk over there and take a sample and measure it in an instrument, way faster than the robot does. And we also just, with all of our senses, it's impossible to totally mimic that with any kind of robotic explorer. So there's a lot of advantages. I forgot to repeat the question. Are we thinking beyond Mars to sending people to Titan, which is sort of relates to the terraforming question, and are there advantages? So yes, there would be advantages, but the Titan environment, as I mentioned, poses a lot of challenges. It's extremely cold. That's the biggest one. And it's very, very far away. And so it would take a long time to get there. So until we, I would say, meet and conquer all those challenges for Mars, it's daunting to think about that idea. But it would be great. I know people who'd volunteer, for sure. Any other questions?
Will the flight plan be predetermined, actively changing, or will it be flying from someone doing it from the Earth?
Question is, would the flight plan, like this video that keeps looping, be predetermined or determined from the Earth? So we call that ground in the loop planning. All of the planning for this type of mission would definitely be ground in the loop, because it would all be based on the data we get on the ground. Other than the first landing, everything after that would follow on the measurements we take, what we learn, where we decide to go. And it's much like the model that we use for the Mars rovers right now. Do you guys in the front have any more questions?